here? Fine. So I guess the people from Venezuela are traveling today, I think.
Tomorrow night.
Tomorrow night? Well, for sure they have a long travel because it's not so easy there. So, I'll start. Any question from the last lecture or anything? Okay, there's something I want to tell you that I was very surprised in the previous class that you didn't know the energy of a water molecule in an equilibrium bath. This is very strange, you couldn't know. So maybe one of the next days we can do a class on statistical physics, on things that I think you should know. Just to see, because maybe these are essential things, in my opinion, that I am a bit doubtful that you have all the background. For example, the canonical ensemble. You have the background with canonical ensemble. But I have some doubts, so maybe we can do an informal class outside one day this sunny, and we discuss about statistical physics a little bit. Out of the program, out of that lecture, out of that course, because I want to be sure the things that for me are essential, basic knowledge, you know. Okay? Because different professors will think different things are essential. So for me, the canonical ensemble is very important because in biology, you are in constant temperature most of the time. So you would like to know what is the probability to find a channel open at a temperature T. So you need to know what is the Boltzmann factor and so on. So just in case one day, sunny day, we go outside in the blackboard and we discuss a little bit. Okay? I won't prepare anything, so I just will discuss with you directly, give you an example and we discuss, because this is important for me, so that you can follow all my lectures. If not, could be it. So
even the class is also always empty. They do not use code.
this class.
It's
Yes.
nicer outside.
Ah, but if it's sunny, we can go outside in the blackboard.
Of course.
Let's use it, no?
Yeah.
It won't be sunny soon. So. Let's go. So, lecture 4. This is the last lecture that I will dedicate. And I'm sorry because I forgot my socks. It's the last lecture that I'm going to dedicate to cell biology with numbers. From next week, I will be talking about stochastic process. So statistical physics for processes that have noise. So I will make a big jump from pure estimates to math. And this is a mathematical basis that you will need for the rest of my course. So that's why I say that next week it would be good to have an informal class of statistical mechanics, complementary to what I will explain from next Tuesday. So today, lecture 4. Would be again cell biology with numbers. Numbers dedicated to times and rates. Again, this will be part of chapter 3 in the main reference that I'm following. This is a long chapter, so I'm not going to discuss all of it, but just what I found most interesting. Right? So, today, the first concept that I will discuss is, again, related to transport in a cell. Imagine this is the cell, the nucleus, and you have a molecule. Or it could be a protein, could be a vesicle, could be. Okay. Think about it as an object in a fluid environment. That imagine it's in position A, and you want to move this object to a target B. So, how do you think this object will move? And how long do you think it would take to reach B? Any idea how will be the motion?
It'll be like zigzag motion.
Zigzag?
Yeah.
You think zigzag? Well, it depends, no? If someone picks this particle, moves it directly. Imagine there is a highway here, and there is a motor that picks this particle. The motor can move it very efficiently, as I discussed in the previous class. So there are machines that make this task very fast. And in a time t, this motor will move a distance xt, it will be b of t. Okay? But most of the times, this vesicle is not attached to a motor, but it's just free. But there is no highway, and you may think how long it will take for this molecule to arrive here. The main point you should know is that you think about it as a problem in physics, that you have a tank of water and you put a grain of pollen here and you wait until it reaches the target. This is a problem called diffusion. You will wait the system to reach its target, but it will walk around and move this type of motion. Okay? This is called Brownian motion. And it's important that x of t will grow differently. So what do you expect? This will be, let's say, ballistic motion. Ballistic. And then, if it's Brownian, what do you expect? How will xt go? So, first of all, xt now is not, this is deterministic motion. This is deterministic. Deterministic means that if I know the initial position, I can predict where the particle will be at a time t. So this means v of t. This will go, you write x of t versus t. You know we're at x0, at time 0, and you know this will be a line. You know at any time where you will be. Okay? This is x0 plus vt. Now, if you are performing Brownian diffusion, you can undo this type of prediction. Now it's different. Brownian is a ballistic motion, it's deterministic, and Brownian motion is, well, random. Random would be like a coin. It's random, a random variable, 1 or 0. The way these processes are called, and this is the introduction to the next lecture, is stochastic. Okay. Stochastic mainly means that even if you know the initial condition, x0, the value at a later time, okay, let me call it t prime, you can do the same experiment many times, and you will be in different places at the time t. There is uncertainty in the motion of the system. So if you look at one molecule, you put a camera and you measure the position, you would do like this in one trajectory. But then you can prepare the same cell and switch on the camera and look at the same molecule, and it may do like this. And then another day it will do like this. It is somehow like in the stock market, no? It's like ragged trajectory. And in other phenomena in physics, but this is what is called stochastic. Means that for a given initial condition, there is uncertainty, there is noise. Okay, so this was first introduced. Okay, so what you expect here is that this has not so much sense this would be whatever, but what it makes sense is to take averages. Okay, average over many trajectories. And now we'll discuss a little bit about how long it takes to reach a target. So here, what you see is that if you want to reach L, you want to reach a target. So the time to reach a target, time for, I don't know, target, let me see, we call it TG. In ballistic motion, it will be L divided by V. But if you do Brownian motion, first of all, it will be different in each trajectory. So what counts is the average. And then, the question I want to answer is this one. How long it takes to reach a given. So, I will spoil you a little bit, but I want you to guess. So, how do you think this will be? Do you think this will go like L? What do you think? You have any guess? What is your guess? So, ballistic will be L. So if you double the distance, you will take double amount of time. Now if you do Brownian motion, if you double the distance, it will be also double. Right? This means if I change L by 2L, the time to reach the target will be twice. What do you think it will come here? You do think, okay, let me say the following. L to the alpha. What do you think alpha will be?
2.
It could be 2. It's a
It
good,
could be anything. Like,
well, anything like that.
not anything, but it will be more than.
You think alpha will be greater than 1.
Yes.
Okay. This is actually what characterizes different processes that are called diffusive, subdiffusive, superdiffusive. You will see. We will see what is the alpha in this
But
class.
if it's diffusive, then there should also be other dependents.
We will see. We will see. Okay. We will see. So this is what I want to motivate this class for you to understand that. Okay, I would expect this to be greater than 1. I would expect that if I go walk at a given speed, I know if I walk at the same speed, I will take double amount of time to reach double distance. But if I do Brownian motion, it means that, okay, I have a probability to walk forward, but also backward. So in the next step, I could do like this, and the next step, I could do like this. Okay, this is a Brownian walker, so it's like drunk, the walk of a drunk person, no? So I expect this to take me longer. So I expect alpha to be greater than 1. This is the main idea, all right? So what I will present to you is the Einstein's theory of diffusion. Of course, the origin of this Brownian motion is due to Brown. Okay, that's why it's called Brownian. So Brown was observing at the beginning of the previous century, was looking at pollen grain. Okay, I don't know how to double pollen grain. This was Brown. Okay, Brown. Looking at the microscope, the pollen grains. And he, by looking at an optical microscope, you can build at home, he saw that this pollen grain in water was doing a very strange motion, and he took notes in his notebook. He started to take notes about the trajectory of this pollen grain, which was doing like this. It was very irregular trajectory, and Brown originally thought that what he was seeing in the microscope was life. He thought that this object in reality was alive. So the pollen grain was really truly alive. Then they started to do different experiments with different particles, and you can put you can put whatever system, a particle of plastic, a particle of glass, and you will still see this motion. So it was Einstein, the person who brought the molecular theory for diffusion, and he said, you don't need life in this pollen grain, but you need that it's small enough so it feels the impact of the molecules around him that are all the time colliding with this bottom gray. But of course, this theory at the beginning was not well accepted. So now we all know this theory works, it's true, and I will introduce this.
Sir,
Yes.
I guess in the expression of average of time
Uh-huh.
for Brownian motion, we need something like constant because the dimension of L to the power of alpha is a distance to the power of alpha, and the others and the
Yeah.
left side.
We need something
We
here.
have time.
Yes.
We need something here. Exactly.
Diffusion coefficient.
Exactly. Exactly. We need something here as well. And this is what I will show you now. What will come here. Okay? Let me put here a question mark. Okay? This is what I'd like to show you now. Because now there is no net speed. The net speed V is 0. But there's something else, the diffusion coefficient. The diffusion coefficient should come here. Actually, by dimension analysis, you could know.
Yeah.
You could know. But let's try to be a bit more detailed and see this. So, Einstein relation dates back from 1905, and it discusses the molecular origin of Brownian motion. It's a beautiful paper, more than 100 years ago. But the story is, as I said, you have a particle that we will consider, for simplicity, it's spherical, so this particle has radius r, and we can think about it like immersed in a thermal bath. This thermal bath is made of many molecules, and this bath is held at temperature T. Okay, this is thermal bath. Thermal bath at this temperature. The particle has radius r, and of course, when you move in a fluid, the fluid has friction. You know this when you think about the free fall of an object. You throw this from a very high, very big height. It will fall. It will accelerate in the beginning, but at the end it will take a uniform velocity. You remember this from your physics lectures? This is because there is friction opposing the motion. So this medium is made of molecules, but it has a friction. This will be the friction coefficient of the medium. Friction coefficient. And what it was observed for many years is that actually I was jumping in my story. It was the following. Imagine you look at this particle and you track its position x. The particle is at time 0 in x equals 0. Okay, so you put your frame reference there. And you look at what is the value of the position at a time t. The position as a function of time will do very similar to here. Will do, okay, let me do a very straight sketch. So instead of plotting x versus t, I will plot t versus x. This is x, and this is t. Okay, I'm just flipping the usual representation. So at time 0, this is time 0, x is equal to 0. I'm starting from here. Okay? And now when time goes, this particle will start to do like this. Jiggle around. So this particle will move like this. Okay? This is x of t. But if I come to the lab on the next day, and I put the particle in the center, and I let it go, it will make something like this. This is from another day. Okay? And if I come another day to the lab, I will see something like this. Right? So now my question is, what do you know about this ensemble of trajectories? First thing is B. What is the average of x at time t? So we take any time here, and we make the average between the values of the position. One is here, another one is here, another one is here. And let me say I make many. So what do you think is the average of all this? Zero, zero. There's zero. On average, you are at zero. Brownian motion means you're having peaks from the right and from the left equally. So, on average, you shouldn't move nowhere. Zero. And now the second question is, what else can we know? And what else, for example, is x squared of t. What is x squared of t? So x squared is like the variance, okay? What is x squared at time 0? On average. Well, all the trajectories start from 0. Okay, the definition of this is 1 over n, the sum I equals 1 to n of x squared t of the I. I is each of these trajectories. Each of these at time 0 are equal to 0.
Yeah.
So the sum of 0 squared,
0.
0, 0. So at time 0, x squared is 0. And what happens if I increase time a little bit? X squared has increased or decreased? Increase. So you see, if you make many of these trajectories, you see they are doing like this. They are like, it's like spreading, diffusion trajectories. They're going like this. Okay? The key point here is that the x squared goes like this to dt. So it's linear with time. Very different to ballistic motion, where x goes like dt. Now x squared goes like t. Okay? So the average square goes linearly with t. And this is called, this d here is a very important quantity. This is called the diffusion coefficient. Okay? This d here is called diffusion coefficient. Okay. So x squared goes like 2dt. So if you plot x of t average versus t, this is 0. All the time 0. 0. But if you plot x squared average versus t, this is a line. Okay? This is a line. This is 2, this, t, and this is 0.
Well, where did the 2 come from? The 2 multiplied the d.
Well, actually, this is the way the diffusion coefficient is defined. It is defined like this. So you can think about it as d. T is defined as x squared t
Yes, just constant.
divided by 2t. Okay? It's a convention. You could call these two together d as well.
Yeah, it's constant.
It's a convention, this. So, okay, does it make sense to you? On this?
the first time that it makes sense to me that why we average over x power 2.
It's the first time.
Yeah,
The first time. I'm happy to hear this. Okay.
I didn't know before why we average instead over x.
Yeah. It's you go to the books, it's there, and you say why, no? But in reality, what you are doing is you have trajectories that spread, so the uncertainty is growing. Okay. In my next lectures, I will give you not only the average and the square, but the full distribution. And what you will see is that it's a Gaussian. The distribution is a Gaussian that is spreading. It's called Brownian or Gaussian diffusion.
Yeah.
Okay, it's very simple, this process. It's the simplest stochastic process, I would say. All right, so interesting question. Well, I could tell you here as well that if you build distributions, they will be Gaussians. But I think you get the point that here times 0, this is x, and this is p, x, p. At time 0, the distribution is a delta function. Okay, so at time 0, the distribution is like this. P x 0 equals delta x. But at later times, this distribution, this is at 0. Then you come here, and the distribution is spread like this. And then you come later, and the distribution gets more and more spread like this. Okay, this will be p of x t with t greater than 0. Right. Now, one question is, okay, I was giving you this picture, but now I said I only look at x. But the particle in reality, it's three-dimensional, and it moves in 3D. So, in principle, this is a simplification of the reality. This is, be careful, for one dimension. One dimension. So now, if I look at two dimensions, then what will happen? I will have x squared of the vector, because now I'm moving at two-dimensional space. Okay, so in 2 dimensions, you have that the particle at time 0 is here. This is x and this is y, and the diffusion is like this. Okay, the diffusion is in 2D. So at any time t, what I define is x vector t, which is xt yt. So I have a two-dimensional diffusion. So what do you think will happen? So let's try to calculate x squared t. What is x squared t? So it's, how can you write this x squared of a vector? I have a two-dimensional vector. It has components x and y. What is the square of this vector? I have this vector. What is the square? You do scalar product of x with x. You get?
X squared plus y.
X squared plus y squared. If you do scalar product of this times this, you do first component times first component plus second component times second component. X squared plus y squared. Okay, this, let me do it. This is x squared t plus y squared t. Okay, and then what do you think it will be this and this? What is x squared t average?
In the respective
Each of them.
Yeah, in the
So
respective-
I have this motion and I project to x.
Yeah.
What is x squared t? 2dt. 2dt.
2D.
So this motion is like I have in the x and the y coordinate this motion in both. So each of them gives me 2dt. This gives me 2dt. So in 2D, x squared is 4dt. Right? energy is a prefactor. In 3 dimensions, what do you think is in 3 dimensions now?
60.
6 dB, because I have 3 dimensions.
So is this 6 related to the fact that there are 6 degrees of freedom? 3 velocities
No.
and 3.
No. The 6 is because each of them gives you 2D.
Nothing else.
Nothing, there's no velocity. In this model, there's no velocity. This is a model that has only x. There's no xv.
But there has to be
Yeah,
velocity.
yes. If you do, okay, this will come in my next lectures. So you can do a model of Brownian motion with inertia.
Yeah.
This model has no inertia. It means that if you did a step forward, there is no correlation with the next velocity. Here, in each step, you flip a coin and you randomize the velocity. This is Brownian motion without inertia, with 0 mass. There is no mass in these equations. It should be suspicious. Where is the mass? So
Yeah.
all will be clarified in my next lectures. Okay? This you will see. Okay? This is just an appetizer to stochastic process. So now you know what is D. I will ask, what's the value of D? What's the value of D? And this is where Einstein came. Because these observations were done already by Brown. However, there was no theory, there was no microscopic theory for this. Einstein came up with a formula for D. What is D? Relating, okay, what is the value of D as a function of gamma T and the radius of the particle? What is the value of D as a function of properties of the system, so properties of the particle, and properties of the bath? You should think, if there is high friction,
There will be.
what happens if there's high friction? Do I move a lot if there's high friction? No, D should decrease when
Yeah.
there's high friction.
So 1/gamma.
I will give you the answer, but the main point is, okay, the main point is, this will reduce the diffusion.
Yeah.
If you increase the temperature,
There will be more.
these guys will move faster.
Yeah.
Temperature, I don't know if you learned this in the statistical physics, temperature is related to the velocity of the particles in the bath. Temperature, okay, this is a bit of a, this is mv squared divided by kV. Okay? And this V is velocity of the bath. Okay, the temperature, you got this in your course?
Yes.
Okay, fine. But of these guys, okay? So increasing temperature will increase the diffusion. Increasing the friction will decrease the diffusion. Okay, so this is a bit of a intuitive. Always when you confront a new problem in physics, you should think about the intuitive. What do you expect? This is useful for you. Okay, so the value of D depends on the properties of the bath. So it will critically depend on what happens in the fluid here. So the fluid can be in different regimes. So you can have your object.
And we into R.
Sorry?
Radius R.
Yeah, the particle plus radius r. Okay? So the radius will be important. You think
Yes,
of big
because
particle,
It won't interact.
you want it diffuse much more. If you take a very small particle, tiny, you will diffuse very much.
Yeah.
So I expect also to be inversely proportional to the radius. Okay, these are the three things I would like to highlight. That Einstein made a relation between D, that word, and this word, the microscopic and the mesoscopic. All right, so to get this calculation, you must know that the particle can move in a bath in a different way. So the bath, let's say you are dragging, the particle is moving in one direction. So then there are flow streamlines of the fluid. Okay? This is like when you see, okay, when you have an airplane and there's the air passing. This is called so-called laminar flow, so you have a flow of the fluid that is laminar, it's like sheets, laminar flow, which happens when there's a number that characterizes this, that is, the Reynolds number is smaller than 1. So to calculate D, Einstein made an assumption. The assumption is that we will work in the low Reynolds number regime. Okay? That is Reynolds number. Okay? So we will be in this situation in which the fluid near the particle, it is in the laminar regime. So an opposite, another limit would be the following. You will have the particle. The particle will move so fast that it will create turbulence. So this will do like this, and this will do like this. Okay, this is when the particle travels very, very fast. There are some, I don't know how you call this, not hurricanes, but there are streamlines. Vortices. This is called turbulent flow.
Yes.
Turbulent flow. That happens when the Reynolds number is much greater than 1. Okay. And what is the Reynolds number? You should ask me, no? The Reynolds number is a dimensionless quantity, which if you go to Wikipedia, for instance, you can see this type of definition. That is the inertial forces, the magnitude of the characteristic inertial forces divided by the magnitude of the viscous forces. And for this type of object, it's given by density, velocity, length divided by the viscosity. Okay, so very important. Density times velocity. This is the characteristic velocity. This is the characteristic length. So here will be the radius. The density will be the density of the fluid. So if the fluid is very dense, there will be a lot of inertia. And this is the viscosity of the fluid opposing the motion of the particle. Okay. To give you an idea, typically when you put a pollen grain in water, this Reynolds number is very small. Typical, very small. And okay, just to see what is eta. So eta is a parameter that can be measured in the lab. This has units of let me see, pascals times second. Okay. When I put a bracket, it means the units. And Pascal times second is, what is a Pascal? It's a Newton divided by meter squared times second. And Newtons are kilograms meters divided by second squared. How do I remember this? Because I use Newton's law. So force is mass times acceleration. So it's kilograms meters second squared. Okay. It's kilograms meter second squared second meter squared, which is kilograms second meter. Yeah, kilograms meter second. And if I do this, I get the same units. Rho VL. Rho is kilograms per meter cube. This is meter per second, and this is meter. If you calculate the units, it should give you this. Okay? If not, it's not a dimensionless number. But do it yourself, just calculate what are the units of this product, and you will see it's kilograms meter second. There is a nice reference that I recommend you to read. Reference, so take a look. It's a very beautiful paper. It's life at low Reynolds numbers. It's full of nice equations, but also of nice drawings. Right, both cells. In the year 1997. Okay, recommended to take a look, to have it there. I'm not going to explain the paper, but it's complementary knowledge for you. Okay, it discusses many biological systems that perform their biological functions in a fluid at low reduced numbers. Right, so I'm going a bit slow, but I think this is good because this is a basis of my next lecture. Okay, and must say I haven't finished Einstein theory. I'm just giving you the assumption of the theory. The next thing will be what is the main result. This is what I'll try to convey now. Okay, with this idea, let's see how far can I go. But this is only the first part of the lecture. So, Einstein found the following relation. That is, okay, we can call it fluctuation dissipation theorem. Fluctuation dissipation theorem. Or Einstein's relation. Is the following. The diffusion coefficient equals kBT divided by gamma. This is what he found. For, be careful, low Reynolds numbers. Okay? You cannot use this relation in a turbulent flow. In this type of regime, which is the one of boiling granular water, a bacterium in the cytoplasm, in water as well, a protein in the cytoplasm. There are no turbulence in the cytoplasm. This would be very crazy. You can have this relation. And now,
This is for laminar.
yeah, for laminar flow. This illuminates a bit what we were discussing before. See, higher temperature, more diffusion. Higher viscosity or higher friction, less diffusion. Okay? When you find a result so close or beautiful, you should think if this makes sense. Always try to get intuition. So again, this is the temperature of the bath. I have it here. This is the friction coefficient of the object in the bath. So this relates system and bath. And this is a universal constant. This is the Boltzmann constant. So just to remember, KB, Boltzmann's constant, 1.38 times 10 to the minus 23 joules per minute. Okay. So now, a trivia question. Where did Ludwig Boltzmann die?
In a car accident.
Yeah, nearby.
And he committed suicide.
Very, very close to Trieste. Close to Duino. Nearly. Right. So, secondly, I will tell you a relation which is called, okay, this is the fluctuation dissipation. This is another useful relation, is Stokes relation. Okay, I think this must be written like this because it's a relation of Stokes. It relates also, this is valid for spherical objects. Spherical objects at low Reynolds numbers. It gives a relation between the friction and properties of the fluid and the object. 6 pi eta radius. Okay? A bigger object experiences higher friction. In a higher viscosity medium, there is higher friction. Fine. And then there's 6 pi. 6 pi is very, I don't know how to call. It's not very aggressive. It's very, it's just a brief. Okay.
I thought it's here viscosity.
Eta is the viscosity.
And R
R is the radius of the object. We are thinking about spherical object. This is R, and this is in a fluid that has viscosity eta.
Is that this?
So, I mean, if you take an object, okay, let me relate this to something you might know. Let's say you have this spherical object, and there is gravity. So there is a sphere, and there is gravity here. Okay, so there is a force, this mg. Now, here I'm saying the mass is negligible, but now I'm thinking it's an example, so I make a bracket. The amount of this is, let's say, a metal ball. This has a mass m. So there is a gravitational force. This is falling. Remember, here there's no gravity. I'm saying gravity is negligible, okay? There's no gravity. I'm moving in a plane, for example, here. And gravity plays no role. If there would be mass, if we would count mass and put this in a fluid falling, there will be this force and this force, gamma b. Right? So the friction, at some point, this object will reach a terminal velocity, which will be, if you equate the forces, will be mg divided by gamma. And this gamma will depend on the viscosity and the radius of the particle. Okay, fine. This is a parenthesis, but I don't want to enter too much in this. I want to show you that you can combine these two equations, 1 and 2. You may do a combination of them and get, okay, remove this, get the so-called, sorry, Stokes-Einstein relation. This is Einstein, this is Stokes. They imply Stokes-Einstein relation, which is D is kVt divided by 6 pi eta r. And this has almost everything we discussed. Temperature, the radius of the object, and the viscosity. Higher temperature, more diffusion. Higher radius, less diffusion. Higher viscosity, less diffusion. So it's very enlightening, this formula. And I wanted to give you a number. Today I'm very slow, but I think it's good you get the concepts right. So you follow this now? Fine?
Yeah.
Okay. Okay, so what I'll do now is to give you a number for the D. So I can do an estimate of what is D in a cell. Well, first of all, for the answer of how long it takes to find a target, now you know the answer. You will go like L squared divided by D. Okay, so for finding a target, the problem I was saying here before, you go from A to B by diffusion. This time will be of the order of L squared divided by D. Okay, this is L. You will be of this order. I'm being a bit approximate, okay? In reality, you can calculate this exactly, it's more complicated. But this is the way it grows, so this you can experiment and find it. Right? So, now I want to say is the following. I will give you an estimate of what. Actually, you have to be very careful because if you do a 1D diffusion, the average time to reach a target in reality is infinity. This works when you are in a closed environment. There are walls. If not, it's infinity. I'll show you this.
The particles didn't get it out.
They get, many of them, they get it. But there are some particles that go, there is a probability of going to infinity. and take infinite time to reach. It's a very interesting property. It's called first passage time, and I hope I have time in my lectures to give you. Tell you. First passage time.
Passage time.
Passage time, yes. I do a lot of research on this topic. First passage time. It's really, really exciting.
Can we have 5 minutes break?
Yes, good idea. Go back to the recording. So, I wanted to give you some numbers about what's the, stop here. What's the value of D of the diffusion coefficient in water? In water. Well, you have all the elements, so you may be able to do everything, even that I give you the formula. But just to give you a brief idea, KBT divided by this. So how much is KBT? You should know, almost by heart.
1.38 into 10 raised to the power minus 2.
But that's K, KB.
Oh, KBT.
KBT should come to you automatically almost.
Why should it come automatically?
I was teaching this. It's a very important number. No one can say KBT.
I don't remember.
300, 300
Oh,
Kelvin?
yeah.
Well, the other day everything was equal to 4, so 40 Kelvin. Nanometers.
Yeah.
Piconewton nanometer. This is important to remember. At 300 Kelvin. Now, okay, this very nice. Next question is, what is eta? The viscosity in water, you can find it online and many references, is 0.89 millipascals seconds. Okay, I'm taking, be careful, the viscosity of the water depends on the temperature of the water. 0.89 millipascals times seconds. Okay, what is this? It would be useful for later to have millipascals in some units that are piconewtons, something like nanometers or microns. Actually, this time I put everything in microns because the typical radius of a example, a protein is of the order of microns. So it will be useful for me to write this in microns, as you will see later. This is what you should remember, 4. So if I want to write this in microns, this will be 4 times 10 to the minus 3 piconewtons microns. You see that 1 nanometer is 10 to the minus 3 microns. And now I take this number, careful because later I'll have here piconewtons microns. I will put radius in microns. So eta in newtons is not good, and in meters is not good. We need to change this unit. So let's see what it is. 0.89. This is what is 0.89 millipascal? Milli is 10 to the minus 3. So roughly, this is close to 1, no? Say it's almost equal to 1. So roughly this will be 1 millipascal per second, which is 10 to the minus 3 pascals times second. And a pascal is Newton divided by meter squared. And this is second. Okay? Final now, which is simple. But as I said, I want piconewtons, so 1 Newton is 10 to the 12 piconewtons. So this is short. Seconds, I'm fine, I will keep seconds, but it would be nice if I can transform the meter squares to micron squares. So 1 meter squared is how much microns? Micron squared?
10 to the power minus 12.
10 to the 12. 1 meter squared
Yes.
is 10 to the 12 micron squared. 10 to the 12 micron squared. How beautiful is this that whatever we take 12 and 12, fine. So this is useful for us because this is, okay, I take out the meter squares and I have piconewtons, seconds, micro square. 10 to the 12 goes with 10 to the 12. So this is 10 to the minus 3 piconewton second divided by micro square. That's the number that I will use. And then I will say the radius is of the order of microns. So with this, we should be able to compute the diffusion coefficient of an object of radius r at temperature in water at 300 Kelvin. This is quite easy. Just apply the formula. T is equal to kVt divided by 6 pi the r, which is kVt 4 times 10 to the minus 3 piconewton micron. 6 pi is 6 pi. We don't care about the units. Eta is 10 to the minus 3 piconewton seconds divided by micron squared. And finally, let me pick r and write it like this, r in microns. Okay? So, this means that if the radius is 1 micron, here I will write 1 micron. If the radius is 3 microns, it will be 3 microns. Anyway, when I do the units, micron will go with micron. This will go up, so we'll have micron squared, piconewton with piconewton, 10 to minus 3 with 10 to minus 3. So I just have 4 divided by 6 pi, which is 0.2, divided by the radius in microns, microseconds, seconds. Okay. So if I have an object of radius 1 micron, it will be 0.2 micron squared. If I have an object of double radius, it will be less. The units in which I'm writing is micron squared per second. So, as an example, if I have an object of radius 1 micron, then its diffusion coefficient will be 0.2 microns squared in a second. But if I have a protein, which is, for example, 2 nanometers, this will be much bigger because 2 nanometers are, it will be 0.2 divided by, how many microns is 2 nanometers?
10
Minus 2.
No,
Careful.
not
Minus 6.
No.
Not minus 6.
Nanometer is minus 10.
Minus 9.
Nanometer is minus
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 9.
nine.
minus 9, exactly.
Minus 9.
Micron is minus 6.
Minus
Yeah.
6.
So 2
Yeah,
to the
it's minus 6.
no,
It's minus 3.
minus 3
Minus 3. Yeah.
because we are writing it in microns.
Yeah.
So this is 2 times 10 to the minus 3. And this will be micron squared per second. This is 2 times 10 to the minus 1. So the 2's go. 10 to the minus 1, 10 to the minus 3, 10 to the minus 2. So it's 100 microns per second. Okay. This is the value. So protein diffuses much faster, but in the order of microns squared per second. That's the idea. Okay. So I hope with this you get an idea of diffusion, very brief idea, and also what is the unit of the diffusion, order of magnitude of the diffusion coefficient in water. So with this I have finished the first appetizer on diffusion, but I wanted to give, this is about energies and times, so I want to give you other examples connected to what I already explained in the class. So I'll now go back slightly on ion channels and times, on how long it takes to pass an ion through a channel. So let me see in the space we need. Okay, I like this picture, so let me stay myself here. Now,
Excuse me.
Yes.
Why the dimension of D is a square meter micrometer?
why? Very good question. Remember that x squared c goes like 2dt. So here the dimensional analysis tells you that d goes like length squared divided by time. When I do this t is not temperature. This is dimensional analysis, length and time. If you do dimensional analysis, you should be able to write everything in terms of length, time, and mass. No more. There's no more. So d is length squared over t. So if you see a diffusion coefficient, you should see it in a unit of length to the square divided by unit of time. That's why there's micron squared divided by second. Okay? This is the main idea, main point. But if you have any question, please ask me now, because I will make a big twist now. But if not, I go to another important quantity related to time, that is the current through ion channels. This is also a very nice example in chapter 3 of the book. And as I said, ion channels are like gates that open and close at random times. This is the membrane, and this is the open channel, by which there is a passage of ions at a given rate. There is an electric current passing through the channel. And this channel, well, remember this was of size 4 nanometers. This is the thickness of a membrane. This channel opens and closes at random times. So we go from this configuration to another configuration that is closed. This is closed channel. And this happens at random times. So you have the channel that is opening and closing randomly. So, okay, when you have this, the ions cannot pass through here. Okay, they don't pass. Experiments have shown that you can measure the electric current through these channels. This channel is, in essence, modeled as, okay, one of these is modeled as something like an electrical circuit, plus minus, there is a resistance, and you can put through it an ampermeter and measure its current, ionic current. So, of course, this you cannot do with a typical cheap electronic system, but you need a very good experiment. And experimentalists show that you can monitor the ionic current through the channel, and it's something that fluctuates. There is noise because ions go in and out, and there are jumps like this. This is kind of, it's called a bistable system, a telegraphic process. I'll talk about this process in my next lectures. This is a fluctuating current in the units of picoamperes. Very important, this is 0, and this, for this ion channel, is of the order of 5 picoamperes. Okay? Of course, there are fluctuations, but on average, you are in 5 picoamperes. Remember, in this picture, this is when the channel is closed, close. Also here, also here, also here. And this is when the channel is open. Open. When the channel is open, there's positive ions. When the channel is closed, there's no. Okay, this continues. And this is stochastic. We jump into stochastic. So now, one may wonder, what is this? This 1 picoampere. The picoampere, it's, what is pico? You have to get used to small units, microns, nanometers, pico, femto. Pico minus 12. And minus 12 amperes. Is 10 to the minus 12 coulombs per second. This is the definition of the ampere. And how many ions is this? So, one ion. What is the charge of an ion? Roughly? 1 coulomb?
Yeah.
Are you sure?
No.
Then? Okay. Okay, 1 coulomb. So we said, what is the charge of an electron?
1.6 10 to the power minus 9.
Yeah, 1.6 10 to the minus 19. So around 10 to the minus 19 approximation.
Oh my God.
Not 1 coulomb, 10 to the minus 19.
Yes.
Okay, that's important. 10 to the minus 12 divided by 10 to the minus 19 is 10 to the 7 ions per second. So you go to the lab, you measure this, you say picoampere, say, oh, fine, this is nothing, pico. But now you count how many ions per second, and it's 10 million. So you open the channel, and they are passing every second 1 million of ions. 1 million, no. 10 millions. This is good to know. So we could try to estimate this theoretically. We could do a theory estimate by knowing very few quantities. Theory estimate. So imagine you don't know this. You don't know the scale of this. You would like to guess what is the, or do a theory of how much current do you have. You can do this if you know a few things from the channel. For example, the following. This is the channel, and I can tell you, for instance, what is, okay, the thickness, so this length, L, this is 4 nanometers, I told you before. The second thing that I will tell you is what is the radius of this channel. The radius. So the radius, let's say is around 1 nanometer as well. What else? So, as I said, we are thinking about passive. There is a gradient of concentration. And this Boris the other day said very well. When there is a gradient, there are more ions here. This goes like this. Okay. So, if I give you another important thing would be what is the gradient concentration? How much? What is the difference between the concentration here and the concentration here? I call this delta C. Okay, delta C. It is of the order of 10 millimolars. So you can have here 90 millimolars and here 100 millimolars. So there is a difference, delta, this minus this is 10 millimolars. Millimolars, as you remember, is mole per liter with milli. So it's 10, this is 10 times 10 to the minus 3 moles per liter. Moles are no units. But you can pass this to microns to the minus 3 because liter is units of volume. And this I give you as a homework. Check, okay? Because I don't need to do all the calculations. This is equal to 10 to the 7 microns minus 3. Okay? You will see you have moles. Moles is 10 to the 23. you have liters and you pass liters to microns cube, you will get this 10 to the 7. 10 millimolar is 10 to the 7 microns minus 3. Okay? What else do you need? Well, I tell you, you need something else. And that's why I explain you this part of the lecture. There's D. You need something else, that is the diffusion coefficient of the ions. The ions diffuse. The diffusion along this axis. And this ionic diffusion coefficient is of the order of, so the ions have size nanometer. Actually less than 2 nanometers, it's smaller. They are around 0.5, around 0.2. So this is around 1000 micron square per second. This is the diffusion coefficient of an ion in water.
I think that's 10 power 7 micromole.
Sorry, let me write down. This is 1000, so 10 to the 3
No, for about.
micron squared second. It's a diffusion coefficient.
I see. For that 10 millimolar,
This is 10 millimolar.
yeah, and equal to
10 to the 7
yeah,
microns minus 3.
micro what?
Micrometer.
Micrometer.
You see why this is micrometers minus 3?
I was thinking about that. This is the dimension of a space, and that's the
This is a concentration. But concentration is a density in the end. Molar is quantity, because a mole is 10 to the 23. It has no units, divided by liter. Liter is unit of volume. So you can transform liter into meter cube, a meter cube to micro cube. That's why. This is a good exercise for you to check. If you can do this, it means you could follow very well my first 2 lectures. If not, come to me and you ask me and I try to solve it. But it is important. These intermediate steps you can try. Okay. Oh, this is bad. Okay, fine. So now, with this, I will say that we can calculate almost everything because we have no space here. So I can go continue this part. So we have this part, and I'm assuming that there is a concentration gradient. So I said this is C of Z, and this is Z, like this, and this is L. So through this gradient, there is current. This is Fick's law, which is minus D partial C with respect to L. So C prime Z. This is Fick's law. Okay. D is what is here, the ion. This is minus D ion times C prime, and C prime is, okay, this is delta C, and this is L. So C prime is nothing but minus delta C divided by L. It's a minus plus delta C divided by L. Okay, this we know, this we know, and this we know. So with this, we can compute the current per surface area of the channel. So this J is per surface area. You can check yourself, because then okay, this will give you actually ions per second per meter square or per micron square. This will be the units of this quantity. Okay, you can check, because this is micron square per second, this is micron minus 3, and this is micron. Okay, so you can check yourself. If you do D delta C divided by L, this will be L squared divided by T. This is D. Delta C is 1 over L cube, and 1 over L, 1 over L. So what you get is L squared L1 divided by L squared T. Dimensional analysis. So this quantity here has units of 1 divided by area times time, which means that the current in the end will be J times the area A. This will give you ions per second. And you can, any question?
I didn't understand what's the C of the C prime of the.
C prime is the derivative of this.
What's the C of Z?
C of Z is the concentration of ions across the channel.
Okay.
We are also assuming this, that there are many ions here, and the concentration is getting less and less and less and less.
Oh yeah, we used here. Yeah, right.
We use here. There is a linear gradient of ions. It's an assumption. So the current, electric current, is the current per unit area times the area. And the area will be the area of the channel. So I said it has a radius r, it's a circle, so we can calculate the area as pi r squared, because it's a circle. Okay, so this will be J times pi r squared. I'm saying just the surface of the channel is a circle. If I tell you this channel is a sphere, it will be different. Whereas I'm saying it's like a cylinder. Okay, assumption. There are two more assumptions. One is a linear concentration profile, and the other is that the channel is a cylinder. Okay. The two things I'm assuming. Right? So given this, say I equals J pi r squared. J is d delta C L and pi r squared. This is my formula. And I'll go step by step. So D, okay, there will be two lines, but don't worry. D is 1000 micron squared per second. Delta C is 10 to the 7 microns minus 3. 10 to the 7 microns cubed. Instead of writing microns minus 3, I put it in the denominator. Did the same. L is, what is L? 4 nanometers. We put it in microns. Better. 4 times 10 to the minus 3 microns times, here is times here, pi r squared, so pi r squared is, r is 1 nanometer, so 10 to the minus 3 microns squared. Okay, you follow me?
J was what? What was J?
J is this. D delta
this formula, what's the meaning of J?
is the current per unit area. Okay, so how many ions pass per unit of time, per unit of area? It's also current. You can define current in different ways.
A lot of different
Yeah.
parameters.
It is physics. So I'm compressing this a lot, so it happens sometimes. Alright, so D 1000, delta C 10 to the 7, L is 4 nanometers, 1 over L is here, pi and R squared. So what we are left with micron cube, micron 4 divided by micron square. I have 1 divided by micron square, and here I have micron 6, micron minus 6. This is very strange. So there must be a problem. Okay, micron square divided by micron cube we get a micron here, with another micron here, micron square, and this is micron square. Fine. Microns are killed. You. So we just get in per second. 1000, 10 to the minus 6, so I get 10 to the minus 3, 10 to the minus 3 cancel, I have a 4, 10 to the 7, so I get something close to 10 to the 7. 10 to the 7, second minus 1. There's nothing else, there's no microns. Microns cancel.
That's a lot of time.
No, this is, it's not a time, this is per second. Per second. So in reality, this is ions per second. But ions have no units, so I can write it like this as well.
But those are still not ions.
Yeah, but the experimentalist told me P compare. And P compare is 10 to the 7 ions per second. So
Oh,
we are victorious. We did a model that makes sense. Okay? This has validation. So this is of the same order of what the experimentalists were telling us, which makes all sense. So we are in time. I don't know if I could give you more, but I think this part I can explain you next day. Will be a big some jump. I believe it's better to end like this, because these are other topics, so I prefer you make me questions and we don't run. I think the most critical thing of this lecture is you learn about diffusion, you learn about transport, passive transport, and you get the point that D is important for many problems. And the other part I will go faster on the next day. It's about the speeds, it's also rates, speeds of motors. So what is the velocity at which the rotary motor in a bacterium goes? Just I give you numbers. And then there's something else about rates of chemical reactions. I think this I can explain you within the part of stochastic process. Any doubt, question from the other side of the world or from the guest house?
Everything is clear.
Next time we will have you here, which is good, and
Yes.
our class will be growing slowly. And hopefully Anna, who is also there, is not there, she can travel to Italy, let's see, let's hope. And yeah, so we finish here. And